We should be. So we'll just let people stream in.
Check the stream. 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 Oh, gonna mute that side. Oh, this is weird because I see myself on a delay here. That's funny. Can you hear me all right?
Yeah, I can hear you just fine.
Okay, cool. Yeah, I see myself on a delay. It's so funny.
Yeah, I know, right?
I'm gonna have to just fully ignore the screen during this.
21 people. Grab my water bottle. We'll wait for folks to stream in, and then we'll get started.
Cool.
Hey, young Philo, I think that's how you pronounce your name. You can't hear me very well? GM. Super low as in my voice is super low, or that I'm quiet? Two different things. Okay. Yeah. Luke, can you say something?
Hey, how's that? Testing my voice, testing.
Can everybody hear Luke?
I don't know if the nice is like, I can hear her. She's nice.
Okay, so you can hear me, but Bushitong or Smart545, can you hear Luke? I know you all can see him.
Do you hear me? Do you hear me snap?
Okay, yeah. Cool. Okay.
That's fine.
Thanks for tuning in, folks. We will get started. It's 3:04 now. We're going to be talking about MEV-Inspect Pi today, everybody. So this is Flashbots' tool for analyzing MEV on the Ethereum blockchain today. MEV activity, what people are doing, where, on what protocols, who's making how much money. I'm Robert Miller. I'm a steward at Flashbots. I also lead Flashbots data, which is where the MEV Inspect Pi product is. And I am joined by the excellent Luke. Luke, you want to introduce yourself?
What's up? I'm Luke. And I've been working on MEV Inspect for about, 2 months now, probably. Formerly was a backend engineer for about 5 years in the traditional web space.
Inopportune time to drink some water for me. Sorry. So MEV Inspect, like I said, is what we're going to be talking about today. So MEV Inspect is our tool for analyzing MEV activity that happens or did happen on chain. It's the third iteration of this tool. Every single time gets a little bit more powerful. We started with the TypeScript library. We had Rust. Shout out to Georgios for that. And now we have this Python library. Currently have support for a couple different protocols. You can see there a bunch of AMMs, a bunch of liquidation protocols as well, and we're looking for help on other protocols too. So this presentation today should give you a sense of what MEV Inspect Pi is, how it works at a high level. Should get some really interesting insights into this too, because we're gonna walk through some of the queries live, as well as do a little bit of live coding, I hope. Just gonna walk through. I literally have 3 slides, and then we'll get to the actual meat of the presentation here. Let me see. Can I do this? This is probably pretty small, so I'm sorry if you all can't read it. But this is a high-level architecture of what MEV Inspect Pi is, how it works at each different step. So we use Kubernetes for MEV Inspect Pi. Shout out to Luke for that design decision. Everything is kind of boxed up in this nice Kubernetes container here. MEV Inspect Pi lives in this red oblong circle here, and it needs to get data from somewhere in order to run. Specifically, it needs traces as well as block receipts. So you have two options for this. You can either get traces from a live node that supports parity style traces. So we use Aragon within the MEV-Inspect Pi team. You can also use OpenEthereum. I would suggest running your own node. It takes forever to synchronize an archive node, but running your own node would be good. If you don't have an archive node, you don't want to wait around for it, you want to get your hands on this earlier. I use QuickNode whenever I need access to a node and tracing capabilities, but I can't use the Aragon node that the MEV-Inspect Pi team uses. And then another thing that we implemented recently is taking data that we've already gotten out of the chain, already gotten traces, block receipts, base fees, other stuff like that, and grabbing it out of a Postgres database instead. And the reason you would do that is because traces take a long time to do, and so it's quicker to just pull the data out of a table if you've pre-populated that. So those are the two kind of data sources that MEV-Inspect Pi can pull data from, either a node or this backfill table kind of stuff. And once you have your data source, you can point MEV-Inspect Pi at a block or a range of blocks or new live blocks, and it'll do its magic of inspecting MEV activity either live or historically. And the way it does that is by taking all of this data that I was just highlighting from you, from your Aragon node or the cache, and it'll pass it into something that we call a trace classifier. This does exactly what it says it does. It takes the raw traces of transactions and tries to classify them. And specifically, it looks at what's the protocol that this transaction, this trace from this transaction is interacting with. Can we infer what function is being called by looking at the function signature? Can we pull out the arguments that someone has called this function with? And with these things, we create structured objects that we call classified traces. So an example would be someone called the swap function on a Uniswap v2 pair with these four sets of arguments inside of them. And on our end, we can tag this structured object with an action that then helps us infer what type of MEV activity it is, right? So if someone is calling the swap function on a Uniswap v2 pair, we know that that's a trade. I think specifically they're called a swap within MEV-Inspect Pi, right? And if I can tag a bunch of different traces within a single transaction as a swap, then in the inspector level, this next set over here, at the inspector level, for a given transaction, I can see we have labeled multiple different traces for this transaction as a swap, multiple different trades here. And I can infer from that it was an arbitrage with certain arbitrage parameters, like it made this much profit going through these four different pairs with these three different assets, and this much this much trade volume across these different protocols, that kind of information, and output us another structured object specifically for this arbitrage to then be able to analyze at a later date. And it'll do the same thing for liquidations in the same kind of style too. So we'll take in those raw traces, we'll try to label them, this transaction had a trace which was calling the liquidate function on Aave with these parameters. And given these classified traces, some of which have to do with liquidations, we can infer that this was an MEV transaction which was liquidating some protocol, and then raise out the information that you might want to analyze that's related to that. And all of this data then gets put into a Postgres database that stores your inspections, the swaps, the transfers. In parallel, it's not really captured here, but we do minor payment data as well. So you'll be able to see how much is a trader taking home from their arbitrage, and how much is the miner taking home in form of payment, right? All of this data gets dumped into a database, and you'll be able to see that. So at a high level, that's the architecture of MEV Inspect Pi. It's a couple different pieces and the technical components that we use for it. So I'll pause there. Does anyone have any questions at this point? Maybe we'll take 2 or 3. Hey Cupid, thank you for tuning in. Okay, doesn't seem like we have questions. So Luke, I will pass the floor, I will pass the baton on over to you. If you could share your screen.
Awesome.
Get into it.
Can you see me all right?
Yes, sir.
Both screens all set? Awesome. Well, let's kick it off then. So I'm going to do kind of a live walkthrough on using MEV Inspect. We're going to do some inspecting live of blocks. We're going to be querying the database to see what sort of insights we can get from Inspect. And then I'm going to attempt to implement an inspector live. This is one I have not implemented before. So you're going to get to see kind of hopefully how easy it is and potentially how not good I am at live coding. So let's kick it off. So where we're going to start our journey today is with this tweet from MEV Alpha Leak. So this is back in July, I think. Yeah. So MEV Alpha Leak basically found this arbitrage that happened where someone did an arbitrage between Sushi and Uniswap, and they went from 70 to 123 ETH. And so as a demonstration of MEV Inspect, what we'll do is we will take this block, inspect it, and see if we can find the same information that MEV Alpha Leak did through sort of manually reading the Etherscan information. So to kick us off, let's start up the MEV Inspect system. I've cloned the repo here, and I'm going to start it up just by running this command tilt up. And so like Robert was saying, MEV Inspect runs entirely on Kubernetes, both in production and locally for development. So we're going to spin up basically a little service for us to interact with MEV Inspect along with a database and, just those two things. So let's go over to the tweet here and get the information we need in order to be able to inspect the block. So to inspect the block, all we need is the block number itself. So I'll grab that, this 1291, and we'll hop back over to the command line. And you can inspect a block by just saying /MEV inspect and then the block number. So let's go ahead and hit that. So now it's inspecting the block. And what that means when it's inspecting the block is that it will basically go to the RPC URL that we've provided to it, either the RPC or cached trace information, pull down all of the traces for the block, which is basically every single function call and then every function call made by every function call, et cetera, et cetera, et cetera. And then from that information, so yeah, we can actually see that here. So we pulled down for this block a little over 1,000 traces. Within that were 222 transactions. We were able to, we basically classified all of them but one, the one being the reward one. We kind of throw out the block reward back to the miner. And then from in that, we're finding these sort of structured objects as well. We found 300 transfers, 51 swaps, and 1 arbitrage. So fingers crossed that that's the one that we're looking for in all of this. So let's go ahead then and see what MEV Inspect found. So these counts are nice, but they don't really tell us very much about the actual information. So what I'll do is I'll hop into that Postgres database that we spun up. And I can do that by just saying MEV DB. So boom, we're in. Here's all the tables that we have right now, all the information. And so let's take a look and see for this block number, what arbitrages has MEV Inspect found? So we can do that by saying, we'll select all the information. Actually, let's switch into the extended mode, a little bit of a nicer print for us. And we'll say, select all the information. Actually, is this big enough, Robert? Are you able to see this? Should I make this bigger? Let's make it a little bigger.
Yeah, you can make it one bigger. There you go.
There we go. So we'll select everything from the arbitrage table where the block number, we're hitting zoom here, is this block. Boom, okay. So we found one arbitrage within this, like it was saying in the print from the inspect originally. And here's the transaction hash for it itself. Let's hop back over to the block, the transaction from MEV Alpha Leak, and sure enough, it's the same transaction. So we were able to pull out the arbitrage from just the block number inspecting all the traces, inspecting all the swaps. From the swaps, determine the arbitrage. So some other information that we pulled out of here, we saw that the arbitrage took profit in, this is the WETH address. And sure enough, we can see that over here as well. 70 Ether in, 123 out. It's through wrapped Ether. Just right there. We can see that the starting amount, if you were to appropriately decimal this, is 70 and then 123, exactly like the tweet had said originally. And then we get some other nice information such as the account address that it circulated on. So that allows us to do things like say, like we'll see actually later in the demo today, who is making, if we were to say, let's look across all of the arbitrages that happened over a block range, who's making the most money, or who's taking profit in, different tokens. How often are they taking in this one versus that one, or exclusively in WETH or exclusively in USDC, things like that. So we can see all sorts of cool information like that. And also I'll say, I'll take a pause to say, ask any questions along the way. Happy to take a pause and describe what's happening. So we can go a layer deeper into this as well and say from the arbitrage, show me all of the swaps that were associated with it. So I can say select star from, actually, we'll select the swap information from swaps S, and we'll say join arbitrage swaps, which is our little join table, arb swaps, on arb swaps dot swap transaction hash transaction hash equals s dot transaction hash and s dot trace address. I should have probably typed this one out in advance, huh? Arb swaps dot swap trace address where arb swaps dot, I'll explain this in a moment, ID equals this one. So we're saying, get me all these swaps from the swap stable joined against this arbitrage swap stable, which joins together the arbitrages and the swaps, where it is this arbitrage, this ID. And there we go. So we've got, I think, 3 swaps here. We can see that 2 of them were one of them was associated with the Uniswap V2 pair ABI, which is the ABI that, the ABI is the interface for interacting with that contract. So we can see that one of them was through a Uniswap V2 pair ABI, which was the Sushi one, and then 2 of them through Uniswap V3. That's through these fields right here. We can additionally see the transaction associated. It's the same one as our original arbitrage. We can see the pool addresses that were accessed, which is kind of cool to be able to see things like which across all arbitrages on Ethereum, which pools are used most frequently, or which ones are used most infrequently. Or you could do it from sort of an alpha perspective to say, and we'll see in a little bit miner payment data that we have, saying something like, which pools on average across arbitrages that were successful pay the miner the least? So we could see maybe, if people think that they have exclusive access to some sort of pool, being able to compete on that pool as well. Of course, where the swap came from, where it went to, and then the tokens associated with the swap and their amounts. So basically all the information to be able to understand what happened inside the arbitrage. And then the last thing that we can, sorry, please.
Double click here. I'm sorry, Luke.
No problem.
So just to double click here, all of this data is pulled out at the trace classifier level, correct? And then, so you get trace classifiers, and they're turned into swap objects, and then those are plugged into our strategy inspectors, which made the arbitrage object that we just saw a little bit ago, right?
Yep, that's exactly it. Yep, so we'll pull down those raw traces. We'll basically say which protocols were they all associated with, attempt to decode their inputs. From the decoded inputs, we get transfers. From the transfers and other information, we get swaps. From the swaps, we get arbitrages. And then all of that just goes into a big database, which is what we're querying right now. Yep. Yeah, anything else on that front?
There was one question. What is the trace address field?
That's a good question. So the trace address field, it basically describes the order in which the trace occurred, or sort of where the trace occurred. So let's actually, we can look at this one, for example. So actually, this might be a bit of a tough example. The idea is this: is that say I call a function called swap, and then inside the function swap, I call a function called transfer. Then the swap function would have a trace address of actually just an empty list And then all children of that call, so if swap calls transfer, would have 0. Maybe I called 2 transfers, let's say. So it would be empty list, and then it would be the trace address of the transfer call would be 0, and then the trace address of the second transfer call would be 1. And let's say that transfer calls something else, then that address would be 1, 0, et cetera, sort of down the line. So basically it describes this tree of the calls that are happening. I don't know if that was a good enough explanation. Maybe Robert, do you have anything to add there?
I don't think I could explain it better. So
okay, yeah. The other and we can use this example actually. So we can see here. So 0020 is the trace address, basically where within that trace tree this swap is called. And because this has the same prefix, this call to the V2 pair, that means that as a result of calling this one, it called a function which called this one. So we basically can see where within the call hierarchy the traces lie. Yep. Yeah, I think that's about as much as I can say. Yeah, within this. Yep. Yeah. Anything else while we're sort of in this data?
So the same person who asked about trace addresses, Palm Frond, I think, says so the trace address and then brackets I is equal to the number of calls at depth I before the current call.
So the depth is the length of the list, and then the order is the I. So for example, some function called another one, which called 2 and then this one, and then called this one. So it's at depth 4. It's at depth 4 here within the call stack. And then within that call, what's the order is the number. Yeah, it's a little bit of an awkward, it's pretty efficient the way that it's stored, but yeah, it's a little bit of an awkward concept. Yeah.
Cool.
Yeah, it's basically a tree. Yeah. Cool. Let's keep pushing ahead. So like I kind of mentioned earlier, one of the most important things that we think that we collect is this miner payment data as well. So I can be able to say, let's select everything from the miner payments table where it's this transaction.
So while you're doing that, just to sort of center, there are a bunch of people who just tuned in.
Oh, cool.
We're looking at an arbitrage that MEV Alpha Leak had on a Twitter page. Actually, if you could link that somewhere, I'll throw it in the chat. You can throw it in our Zoom chat here.
Yep, I'll do that.
So this arbitrage that MEV Alpha Leak linked on Twitter somewhere, and then we ran that the block that this arbitrage was in through MEV Inspect, and now we're looking at some of the data that MEV Inspect outputs into a database. Luke is walking us through it.
Fantastic. Yeah, and so where we are in looking at that is we just looked at the arbitrage itself, sort of the profit information around it, and then the swaps that compose it. And now we're looking at the miner payments data. So we're able to see how much was paid to the miner, basically. And an important piece of this is that we look at two main forms of payment to the miner. One, which is the one that I think most people think about, which is gas payment. So I can pay the miner directly just through making a large gas fee. And then the other thing that'll happen is that searchers will actually make a direct transfer of ETH to the miner's address, to what's called the Coinbase. And so if we walk through this, we can see that the actual gas price associated with this, how much gas was used, or how much the searcher paid in gas was 0 for this, which is totally fine to do, as long as the miner ends up making some form of money. And instead, all of the money was paid directly through a transfer of ETH to the miner. So this person, it looks like transferred, I think, 48 ETH if we look at the decimals. Whoops, right? Whoops. Sorry, my screen is in the way here. Times 18 won't do it. Yep. So that was 48 ETH was sent to the miner directly as a result of this arbitrage. And so I think the original amount was, what was it? 123 minus 70, so 53. And then they sent another 48. So there's a net profit of 5 ETH for the searcher for having executed this. Some other information that we store here. This is an older block, so we don't have the base fee, but we have the 1559 base fee associated with it. So we can see sort of net of the base fee, how much was paid to the miner, which is in the post 1559 world, how much actually goes to the miner. The rest gets burnt. We have a gas price adjusted with that Coinbase transfer. So we'll take the sum of the gas price times how much was used, plus this transfer, divided by the gas used again to get basically the effective gas price. So they paid none in gas price, all in Coinbase transfer. So this is the effective gas price, the effective price they paid per gas. Yeah, I think that's along with the transaction for the actual payment. And I think if we go back to Etherscan, we should see that this lines up as well. There's that 53 amount that we did, or sorry, there's the 48 amount that we were just looking at there. And then an actual profit amount.
So we got a question in the chat here from, I can also try to put my camera on when I'm speaking. There's a question in the chat from somebody here, Godo Koro, I think. It says, why have such a high bribe? And then is it competing with other searchers? So yeah, that's precisely the reason why the miner payment is so high here, is because there were a bunch of different people that were competing for this. And so you needed to pay a high bribe because others were also paying high bribes, basically. So yeah, you were right that it was because they were competing with other searchers.
Yep. Yeah, and if you want to dig a little bit more into the miner payment aspect of it itself, I just posted a thread last week looking at some of the aggregate data around miner payment as a percentage of profit, and in some other lenses to be able to see sort of how are searchers in general thinking about payment to the miner, and how much do they usually pay. And the sort of spoiler is that it's roughly around 90%, some up to 97% as a percentage of profit if you look at it through that lens. So it's pretty competitive at this point. Yep.
And there's a follow-up question. Well, two things. So Luke, what's that gas price with Coinbase transfer in Gwei? I think it's 2004, but so it'd be divided by 10 to the 9th.
10 to the 9, yeah.
And then someone asks, how do you know what is a competitive bribe?
Yeah. 200,000.
Oh wow.
That's a good pay.
Yeah, I wonder what the highest gas price transaction has been ever.
Would you like to see in a minute?
Oh yeah, that's a good point.
Let's do it.
So, how do you know what a competitive bribe is? The only way you know what a competitive bribe is by analyzing historical opportunities and like what other people have paid. The strategies that bots use to determine their payment to miners are they are pretty repetitive. So some people will just pay like a X percentage out to the miner every single time. And as a result, like you have a pretty good sense of what people are paying each time. Yeah.
Cool. Any other questions? Take a pause here. This will be kind of the end of our inspecting of a single block, and from here we'll go and we'll actually look at some of the aggregate data we can see from running a production for a little while.
Yeah, let's go ahead.
Let's do it. Awesome. Yeah, I can't see the chat. Sorry about that, folks. So I'm relying on Robert as my eyes. Cool. So we'll hop out of there, and what we'll do is we'll actually just switch over into. We'll actually switch. So right now, like I said, we're running on local Kubernetes, and we have a production deployment of Kubernetes as well, where we can run all these sort of same queries using the same interface. And you can too if you choose to deploy it. So what I'll do is I'll switch my context over to our AWS deployment of the FlashBots cluster. And now, in the same way, I can just run MAVDB. Only now I'll be connecting up to our production database instead. So we'll just give that a second. Cool. Select one, just make sure we're good. Yep. Maybe select count star from swaps. Yeah, that looks like it. Cool. So let's answer some larger questions. So here it's neat to be able to go to maybe Alpha Leaks tweet and say, oh yep, we can get the same information that was found through digging through the Etherscan. But what's more interesting about Inspect is the ability to automate that process even more, to be able to say, I'm not going to read anything that comes in. I'm just going to, maybe let's set up some notifications for interesting things that happen, or maybe I'm interested in trying to understand how should I price, if I'm a searcher, how should I price my gas for an arbitrage, between these two pairs? How common is that? Has anyone ever done that before? Or is this a novel opportunity? All those sort of questions. So let's start actually with the one, coincidentally, that you mentioned, Robert, around, or someone in the chat might have mentioned around the highest ever miner payment. So I think it'd be cool. We'll do the highest ever miner payment is actually a little bit of a tainted question because we'll often see miners who will just pay themselves. Well, actually, we could just do it. Let's look at the highest miner payment ever. And most likely what it's going to be is just a transfer of the miner between kind of some of their accounts. You'll just see it's only a transfer of the miner of like maybe 5,000 ETH. But let's try it just for the sake. Select star from miner payments where order by gas price with Coinbase transfer. So we're going to include both forms of the gas price, both the gas price itself and the Coinbase transfer divided by how much gas was used to get a relative price there. And we combine those two together. Descending, limit maybe 10. So we'll get the top 10 ever payments. Boom, here they are. This is a little bit messy. Let's get just how about maybe the transaction hash, and we'll get this gas price. Make it nice and clean. Boom, okay. So this is, at least from what we've inspected so far, which is I think around probably like 100,000 blocks or so. The highest ever. So what is this in Gwei? Let's see. 10 times 9. Oh my, what is that number? Is that billion? 27 billion? Let's take a look at this transaction from just a quick Etherscan perspective as well. Oh, interesting. This actually, I don't think is a
liquidation. Yeah.
What is this? The liquidation?
Yeah, it's a liquidation. I've seen this before. It's like this is the highest paying, or well, it's the highest paying MEV extraction. I think until a few days ago it was.
Wow! Until a few days ago.
Yeah.
See, I guess we've shown our hand that we're a few days behind at the moment.
Yeah.
But there we go. Okay, very cool. Look at that. It was new to me. It wasn't new to Robert, but it was new to me. This cool liquidation. Good thing we checked. How about another one here? Highest gas price ever. So this is more of what I was kind of expecting, where we're basically just seeing, what is this, 11 ETH transferred straight to Ethermine. So something else that we can do, maybe, so liquidations are one way of earning profit. Maybe we want to look at not just arbitrage, but look at sandwiches, just sort of anything involving swaps. Then what we could do is say, let's take this exact same query and we'll just join it against the swaps table. So we'll say, I want to find all of the miner payments, so the most expensive miner payments, just like this. Oops, actually, wait 1 second. Don't do that. So we'll select the transaction hash and the gas price again. Coinbase transfer. Only we'll join it against the swaps table, because then what that'll tell us is show me the highest gas price, top 10 that we've seen so far, gas price, where there was a swap involved somewhere in the transaction. So that'll be things like arbitrages, back running, et cetera, et cetera. So miner payments, let's call that M, join swaps S on S dot transaction hash equals M dot transaction hash order by gas price descending, and only 10 of them. Oops. Oh, we got to be specific here as we share that field. Okay, cool. So here is the highest there. Oh, we could probably do distinct as well. That might actually slow things down quite a bit. That's okay. We'll distinct with our eyes. So here's the top miner payments by gas price for all transactions that we've seen so far that involve a swap. So maybe we can check into this one a little bit more to get a sense what happened. Is this the same? Oh, this is the same one, right? How about this one? But hopefully this will filter out those other ones involving direct payment to the miner. So let's see what this one was. Borrow 20,000 Ether from DYDX. That's quite a bit.
So,
and then it looks like 0x in Uniswap. Oh, cool. We just added 0x support, right?
Yeah, like very
nice.
recently.
Like literally, like last week.
So
That's cool.
here's a little bit of alpha here for the watchers. This person doesn't want to have any inventory, so they are taking a flash loan. They don't want to have an inventory. Also, you're dealing in like the millions of dollars here, right? So they needed $1.8 million worth of ether in order to capture this ARB. So they're getting a flash loan from DYDX, and DYDX charges you a one-way fee, regardless of the amount that you actually need to repay them. I'm sorry, regardless of the amount that you borrow. So whether they were borrowing 489 ETH or 20,000 ETH, like the payment is the same on DYDX. And it actually costs like marginally less gas, I think, to not have to input the amount of data that you are, the amount of ETH that you need from DYDX. So they have hard coded in here, I'm going to flash loan, $74 million from DYDX every single time that I am arbing something, like regardless of how much you're actually using from it. And this is different than other flash loan services like Aave, for example. Aave, you need to pay some fee. I don't remember what it is off the top of my head, but some fee proportional to the amount that you're flash loaning from them. Yeah. So that's why you
Very
see
cool.
like 20K here. They actually only use 489. Yep.
Awesome. Some live alpha, just like that. Little live block explanation.
There you go.
Hell yeah. Cool. And I'll leave the rest of these you can kind of explore in your own time, or you can ask. Maybe I'll share this. I'll share some of these lists after the stream as well. So another thing we could do, kind of a question that we get asked for a lot, is which searchers are making the most, just like overall, how much are they making? And it's tough to say overall from a profit perspective. That's something that we're kind of working towards, being able to say more just generally, just in terms of how much transfer, how much was like net transferred to them in a transaction, but it gets complicated. But one of the questions we can answer is which searchers are making the most in arbitrage, at least every arbitrage that we're able to see. And we're adding protocol support every week, as you can see with that 0x1. So for this query, it's actually a little bit more complicated. So I'll do a copy and paste in just to demonstrate kind of the level, how far you can kind of take this this exploration. I've got it in my MEV TV directory right here. Here's the top searchers query. So cover your eyes for a second here. This is obviously, or sort of, don't worry about reading it quite so much. I'll do a walkthrough in just one moment. Let me try to break this out since it's getting a little bit. Okay, there we go. So some of the things to consider. We include information about whether or not there was an error somewhere in the trace. So we'll get all information about for each ARB, whether there was an error somewhere within it, because we want to exclude those. We also can do things like, let's exclude sandwich attacks for now, because sandwiches actually make it a little bit tough to see how much was net made. Like you might do an arbitrage that massively shifts the price and causes for you either like a massive loss or a massive gain, just to then on the other side pay it back. So we try to filter those out as well in this analysis. So we'll skip anywhere you're doing an arbitrage on one side of someone trading and then doing something else on the other side. We'll skip all those. We'll just say you just did an arbitrage within this block.
And for those of you who are watching this
go for it.
in posterity, that's a sandwich. So we're trying to filter out sandwich attacks here, basically.
Yep, exactly. And then we'll join against this miner payments table as well. So we'll see, let's find all the ARBs where there are no sandwiches. So we're looking for without sandwiches and where there's no errors as well. Let's see. Oh yeah, and not any errors. So no sandwiches, no errors, just pure arbitrage, and just group it by the account address. And what we'll get is the profit from the arbitrage itself, along with how much was paid to the miner in total, which is the gas price times the gas used. And then we'll also look at the net profit, which is how much they made in total minus how much they paid to the miner. We can sum that over all the blocks we've ever seen, and then group it together by the accounts, order it, and we'll get the top 10 most paid searchers as seen by MEV Inspect so far. Let's try it out. Okay, here we are. Let's see. This one might take a second because that's a pretty beefy query. There we go. Oh, luckily we Got a lot of good stuff here. Okay, so here's the winners as of right now, supposedly. We've got some familiar ones in here. We got obviously a bunch of leading zeros. No surprise there. Let's see. This searcher has made how much net profit so far according to MEV Inspect? 10, 18. What is that? 139. What is that? What is that right now? It says 500K, which is probably a little bit of a low estimate.
Over how long?
This is over probably what, 100,000 blocks, I would say, or maybe 50,000 blocks.
100,000 blocks, so 25,000 minutes. So that would be
We get the calculator collab here.
400 hours, right?
400 hours.
400 hours, so 10 days? Question mark?
That's pretty good. 500K every 10 days.
500K
I wouldn't
over
mind.
10 days. That seems aggressive, but
That's too much, you think?
yeah, I don't know.
I don't know. Okay.
Somebody in
well,
the
we can
chat
look
can do
into
that
it.
calculation.
Someone in the chat.
Someone in the
check
chat, figure out how
calculation.
long 10K blocks is for us.
I might be
please.
wrong with that. Well, let's see. Select. What can we actually check? I don't know if I can. If I count distinct blocks, I think that might. Well, let's try it. How many blocks are we actually looking at? Select count distinct. So we're doing it live here. Block number from minor payments. What? Select distinct. I think I can't do a count distinct. Is it? Oh, it needs the. Postgres is very picky, I think, about this. Count distinct. Okay. Yeah. Let's see, this might take a little while. We'll give this about another 15 seconds. Are there any questions in the chat while we're waiting?
No, not right now. I'm watching the chat.
Not right now.
Oh, sorry.
Anyone?
Does minor payment include transaction fees, not Coinbase's?
Yep. Yeah. So it's transaction fees and and Coinbase basically. We have all the we have so the base fee, and then you have the gas price, and you can get the tip amount from base fee gas price minus tip, and then we also have the Coinbase transfer. So it should all be in there. Yep.
Hey, Georgios, what's up? Thanks for tuning
Take
in.
a minute. Georgios, what's up? Okay, I think this might not finish on here. This is quite a big query,
Yeah.
but people will go. But I think it's about 100K blocks that we're looking at. Yep. Awesome. Well,
So
that's all.
we got
Sorry, go for it, please.
one more question.
Yeah.
Palm Frond asks, so the first step to analyzing a new opportunity using MEV-Inspect would be to write a trace classifier. So if you wanted to add support for new types of MEV, that would probably, if you wanted to add support for a new protocol that's not already supported, you would write a trace classifier. This is right. If you're talking about some like net new type of MEV that isn't an arbitrage or isn't a liquidation, or maybe it's like some combination of the two, then you would need to be a little bit more involved. You need to write a strategy inspector, but you can plug in pretty easily and write a trace classifier. You'll see us write one live, I think after this, yeah.
Mm-hmm. Mm-hmm. Yeah, this is the end of sort of the query portion. So anything else on the querying side or anything that's come so far, any questions we can answer right now. But if not, then we'll dive into the live coding.
Georgios, we got V3 classifiers already. Had them for a little bit.
Easy.
Easy.
Been there. It's because Python's so much easier to use than Rust, I think. It's a very flexible language, very... No, just kidding.
Says somebody A98,000. Last thing, and then we'll go on. A98,000 says 100K blocks is like 16 days, sirs. So the total net profits that you see here, 139 ETH, 130 ETH, 104, 95, etc. That's over 16 days.
Let's take a look at this person on Etherscan, maybe just to see.
Yeah, and then I think we should...
2.7 million. I mean, that's maybe possible, maybe doable, right?
Yeah.
We're doing...
They love wrapping and unwrapping Ether, I guess.
They love wrapping and unwrapping.
Yeah, well, you can see unwrapping and throwing.
Just sort of a hobby of theirs. No arbitrage, let's just do a little wrap unwrap.
Let's move to live coding.
The live code. Let's do it. Awesome. So we will hop out of here. Cool. So I'll switch back to my local development system here. I don't know, do I have Tilt up already? Yep, so all good on that front. And we'll just close out here. Yeah, and so, so next I just want to show kind of how easy it is to add support for a new protocol. So like Robert was saying, there's kind of different levels that you can contribute to MEV Inspect on. And probably the simplest level, but still extremely powerful, is just adding new protocol support. Basically giving us the ability to decode a trace and then be able to query it, basically. To show that, so the goal of MEV Inspect is to illuminate the dark forest. We're trying to make it as open and clear as possible what's happening on Ethereum. It's out there already. It's just about being able to index it and query it, basically. So we thought, since there's been a lot of discussion recently around just token airdrops and kind of fairness of that, or whether, sort of what's happening around people using different protocols, we thought it'd be cool to implement support for Ribbon and then look at some of the deposits that have happened through time, do a big backfill for that. And also a disclaimer before we jump into this. Truthfully, I have not written this yet. So I did pull down the ABI in advance. So if we run into trouble, just know that that's what's up. But I think we'll do just fine.
It's a real live coding session.
This is real live coding right here. Yeah, this is my hands are shaking a little bit. This is true. Okay, but let's go for it. So let's check out maybe a new branch. We'll call it Ribbon. Cool. So here we are in the repo. And what we'll do to start is, yes, we're already on local, right? Let's just make sure. If I look over at Tilt here, I think we're doing well. Yeah, let's maybe restart. I don't know if I said this clearly earlier. Tilt is our system for running Kubernetes we use a system called Kind for local Kubernetes, our local Kubernetes cluster, and then Tilt basically does the reloading of stuff. So every time I change the code, it will sort of hot patch things for us as we're going. So yeah, so that's running well. That other one, yeah, okay, yeah. So here we are on Ribbon. So we'll start out by adding the support for the ABI. So for those who aren't familiar with ABIs, basically they just describe the public interface to a contract. And so by having that public interface, that's all we need in order to be able to decode from the traces and the transactions, what was actually called, which functions were called, things like that. So I pulled down the ABI for the Ribbon Vault, and I just added the deposit functions for now, just to make things super simple. So we've got 3 functions that we'll add support for: the deposit ETH function, and the deposit for, so depositing for someone else. Make sense? And also, like I said, feel free to ask questions along the way here. So the first step towards this, you hop into Inspect By, is we'll move the ABI into MEV Inspect itself. So we have a big directory of ABIs here for all the different protocols that we support. So we'll make a new directory here for Ribbon. Boom, nice and empty. And then we'll copy it in from above where I already have it. And if you're looking for ABIs, you can usually get them off of Etherscan. I actually have a little utility for it as well that I could share out after this too, where you can just fetch it with an address and it'll fetch it from Etherscan. I think, where is it? Up one more. Boom. There it is. So it's in this little Ribbon directory. And then in order to hook it up to MEV Inspect itself, what we'll do is first we'll add support for it as a protocol. So inside MEV Inspect, I think, is protocol its own? No, I think it's in block. Let's see. Oh, no. In the schemas. And then what do we have? See, true live coding here. Block. It's not in block, then it is in classified traces. That would make the most sense. There it is, protocol. So here's all the protocols that we support so far. So we'll add a new one for Ribbon. Just like that. Boom. And then we added the ABI to the folder already. And now what we'll do is we will simply describe to MEV Inspect, hey, here's this new ABI I have. It's associated with the Ribbon protocol. Please go ahead and just decode for us with it. The way we do that is with something called classifier specs. So in MEV Inspect, classifiers specs. We have a bunch of these that exist already. Let's take a look at maybe the WEF one. It's pretty straightforward. So here's the classifier spec. We give the name of the ABI, the protocol it's associated with, You can optionally provide a list of valid contract addresses, which I think we'll do here for Ribbon, since I think they only have a fixed number of volts deployed so far. And then you can optionally add these things called classifiers, which will auto do decoding from a function call into a more of a structured object. So here we're building actual transfer objects, which are helpful for kind of decoding swaps and then arbitrages, et cetera, et cetera. Those sort of structured objects that end up in their own tables. That's where these all come from, is these classifiers. But we won't be concerned about that for our Ribbon use case. So I'll keep this open while I build the Ribbon one as well. So if we go MV inspect, gonna move my little camera here. Classifiers, and then inspect, and we'll make a new one, ribbon.py. So we'll want the protocol. We'll want some of these things. Let's see. We want the protocol, and I think the spec. That's actually it. Make these a little simpler. Cool. And then we want the, we'll call this the ribbon volt spec. Let me move this little zoom thing here down. Okay. So we'll call this the ribbon volt spec equals a classifier spec. And it takes the ABI name. What was our ABI name again? Spec ABIs. Oops. Ribbon fadeable, okay. No need for the JSON, whoops. Okay, along with the protocol, which is the new one that we just added. .ribbon. And then valid contract addresses. Like I said, I'll grab these as well. Equals, we'll call this ribbon volt. So in the future, we might want to add support, like, you know, if a new one gets listed, then we get it automatically or things like that. But for now, we'll just make them fixed for the sake of demo. And I think we can get these from their website. Head on over there. Finance. Any questions in the chat so far, Robert?
No, just a couple comments about how quick you are. So
let's go. Power of Vim. Vim Adventures. If anyone wants to get into Vim, Vim Adventures. I did not write it. I get no money from them. They just helped me a lot.
This is not sponsored.
What is this? This is wild. You want to see some really crazy stuff? I'll do. Check this out. 0x. You got Vim. Oh, I can't even copy it here. What is wrong here? Isn't it right? Am I crazy? I can't drag it?
Yeah, it doesn't look like it.
Okay, I guess we'll just open each one. All right, that's fine. Live coding, folks. Live coding. This is how you know.
Oh boy.
Okay, one sec. We'll just paste all these in here for a sec. Oh my goodness. The bells are going off. It's getting crazy. What do we think of this? This is the best part of the whole thing, huh? Oh my goodness.
How many times have you done something like this?
I don't know, I guess. This is the real, truly, I will say Vim will change your life. I didn't mean for this to be a Vim side advertisement, but this is the sort of stuff that, you know, we'll just throw it up here. Whoa, whoops. What did I just do there? It'll change your life and then it'll cause you to make big mistakes. The zoom elements are honestly the toughest part of this, so they're getting in the way. Should have done the swap dollar, but that's all right. Okay, there we go. So we got our addresses. So now we have valid contract addresses of the ribbon volt ones. We have the spec here. And then the last thing to do is we'll just import the spec into our list of specs. We probably want to do this more automatically in the future. I mean, really in the future, we probably want to move this all to a big database, but rather than having all these just living in the repo, but not there yet. We'll get there. Okay, I think specs init maybe. I don't really like putting them in the init, but okay, .ribbon import ribbon vault spec, and we'll just throw it in our big list here. Ribbon vault spec, fantastic. Okay, so how you know? Did you just laugh at me? We're in there. Okay, let's close out all of this business. So let's take a look just to see what we did here, just to make sure we didn't Not making any mistakes. Okay, so we have, we added the Ribbon Vault spec to this list here. We added a new protocol for Ribbon. What else did we do? We added this nice new, whoa, is that up somewhere? No. Let's recover it, I guess. Yeah, okay. Here it is. We added the new Ribbon classifier spec. Fantastic. And then we added the ABI, right? We list the ABI. Boom. Okay. So that actually should be everything we need in order for MEV inspect to pick up on all those decode functions when they happen and throw them in our nice classified traces table. So let's give it a shot.
So,
oh, sorry, please.
Either right now or in parallel to what you're doing, just can you review the things that you did there? What were the steps to get to this point? Definitely.
So what we did was we added, whoa, 1 second. So we added the ABI. We added a new directory. So let's hop into this ABIs actually again. So here's all the ABIs. ABIs are the public interfaces for interacting with contracts. So we added a new set of ABIs for Ribbon. We just added the one for support for their Vault, and we just added support for the deposit one as well, just to keep it super, super simple. And then from there, what we did was we added the classifier spec itself, which is in classifier specs Ribbon right here. Whoa. Right? Oh, oops. I don't know. I don't really like this. Yeah, editing this. Can I kill the file? Let's kill the swap file. Sorry, that's Vim stuff. You won't have to do that. Okay, great. Yep, so we added a new classifier spec where we specified the ABI, the protocol. We added another entry in our little protocol enum as well. And then the listed valid contract addresses associated with the Vault. Yep. And so that's I think that's everything, right? Yeah. We'll find out in a second.
Let's
so
see.
what I'll do, yeah, go for it.
Just saying, let's see.
Oh, you say let's see?
Yeah.
Oh, whoops. I lost these little things at the end. That's okay. We'll use a little Vim magic. Boom, there they are. Okay. So I'll take one of these and let's just look it up in Etherscan and see if we can find a deposit call. And then we'll analyze that block and see if it ends up in the classified traces table. So boom, we're here. Deposit. 4 hours ago. Great. We'll take it. So someone did a deposit. Do we have that information again? Deposit of some hex amount. Okay. Well, we'll find out. Right? Is this the? Yeah. Okay. So we'll grab this guy right here. This block number, and just like we did at the very start, we'll say MEV inspect in that block. Whoa. What was that last number? 6. Let's take a look.
So we're pulling data live from some Aragon.
Oh, block not found.
Block not
might be a little behind that Aragon node. Rip. That's okay. We'll grab this one. How about? There we go. Classified traces. Boom. Okay.
All right.
Fingers crossed. Let's see if we found it. So here we are. So we're in the database again, and we'll do select from our classified traces table. This has actually, let's just take a look at this table for a second. It says everything we learn about a given trace. Oh, that's a little bit messy, huh? Boom. Okay. So it's got all of the information associated with the given trace, its block number, trace type, things like gas, etc., along with the decoded stuff if we're able to decode it optionally. So that would be the ABI name, the protocol, function name, the inputs, etc. So let's take a look here. Whoa. Or whoops, no, we want that. Well, 1 second. We spin up a pod within Kubernetes actually just to do the database querying to keep everything inside the little zone there. MVDB. Nice. Okay, select star from classified. Let's just see how many we got, just to make sure we did in fact inspect the block. Traces, where block number equals, whoa, function name. This one. Okay, there we go. So we got the 1,000 traces. And let's say protocol equals ribbon. Fingers crossed. None. Damn. Let's see, did I specify the valid address is potentially wrong? Let's take a look here. Well, we had a deposit. Or did this not match the actual signature? This was a UNT 256. Let's see here. For the vault addresses, whoa. This is one of them, right? Interacting directly with this. 5A83. Let's take a look at the other vault addresses. There's a chance that I might that we might need to make them lowercase. Although I think we handle that automatically, the lowercase or uppercase. Balancer have some distinct ones. Let's see who has a list of what does, right? Is it lowercase? No, it's uppercase. Okay, we're switching from live coding to live debugging. Let's get rolling.
Let's go. Truly live coding, like we said.
Truly live coding, yeah. I'm sure it's going to be something silly I did here. Well, actually, let's take a look. The other thing we can do, we can take a look and see what did we see about this transaction in general. So select star from classified traces. Where transaction hash equals, equals the one that we're trying to get. That's a mess. It's still a mess. Okay. Oh, but look at this. There it is. Protocol.ribbon. Is that how it writes? I guess so.
Yeah. So
there we go.
Not live debugging. There we go.
Not live debugging. just it was the live querying that got me. That's kind of weird. That should just say ribbon. That's weird that it says protocol dot. I thought we didn't have that. Oh well, sure enough. Here we go. Well, let's query for it by, let's do that then anyways. Select star from classified traces where protocol equals protocol.ribbon. Interesting. Cool, so it looks like we found a couple actually. So there was the one, or did we find it twice? Did it happen 2 times? Where's the trace address?
No,
I think it might show it, whoops, what's that?
Looks different.
From address is different here. Yeah.
Yeah, well, no, same deposit number though. Same deposit number.
Same transaction hash. That's the thing that's weird.
Oh yeah.
It might have been, did they call it twice? I don't know. It's possible. So one of the things is that this is a proxy contract, I know. So I wonder if it's calling, but it should be a different address for the valid address. Yeah, it's the same amount.
Well, so the first one, the from address goes to 0x65 as the 2, and then 0x65 to 0x67.
And then 0x goes to the 2.
So it must be a proxy, cool. Yeah. But
interesting.
Let's not dwell, I think, since we're running low on time here.
Sure. Well, we can go back to the trace address as well and see that it's a subcall. Yeah. There you go. Yep. Yeah. Okay, cool. So maybe we can filter to only looking at the ones where the trace address is at the top for now. Second, so next to me. Okay, cool. So, so we added support for ribbon. That's cool. We can see the deposits. Now let's kick off maybe a round of looking at it over a larger range. What I'll do is I'll actually just deploy this code to the production system right now. Get a little deploy script in here, pushing it up to AWS. We have a repository there, and then from there it'll roll over in Kubernetes to use the latest code. I might take a second here. Any questions while we're going along here? Any questions on that process of making the inspector?
So Georgios asks, how do you go from parsing a set of traces into an MEV category?
Into an MEV category, like the transfers and swaps and arbitrage, things like that?
Yeah, let's go each step of the way. So traces to swaps to arbitrage.
Totally. So there's kind of a couple different ways that we can think about this business over here. A couple different things we can think about. So there's one where there's sort of a base level of like, maybe if I did I forgot to switch back to production. This context. Oops. Flashbots, okay. We're deploying to our local Kubernetes. So yeah, there's a couple different ways to think about it. There's one which is, let's actually look at that WETH one again to explain. So in some cases, from the actual decoding of a trace itself, we can get a structured object out of it, like this transfer object. So when someone makes a transfer, we also write to, we build this transfer object up here, which has sort of simple information like to, from, the associated token address, to make it easy to use later on. So transfers work like that, and swaps also sort of work like that. Although swaps, let's take a look at a swap. For swaps, it's similar in that you say, where is it? Classifiers. So this swap is a Uniswap v3, uses the Uniswap v3 swap classifier. And what the swap classifier requires is that you define who the swap recipient is. And from there, it uses the transfers that were already parsed within the transaction sort of elsewhere, plus the recipient, to determine everything it needs to know basically about the swap. So there's some of these objects that are defined at sort of this classifier level, where we'll parse them almost directly out of the trace itself, transfers, swaps. And then in other cases, we'll take that stuff that was parsed out and then use it to like infer more information, like for the arbitrage case. Let me make this maybe a little bit more tangible too, I think looking at it from a top-down level. Looks like we just deployed as well, so I'll get back to that in a second. Here's an example of what happens when we actually inspect a block. So we'll
maybe
get the information.
Maybe like the backfill of this.
Sure.
running,
Yeah.
And then we can answer this through that, because I'm mindful that we're over an hour now. So.
Okay. Cool. Yep.
Yeah. Sorry.
So okay. No problem. Good call. Okay. Yeah. So one of the things that we've been working on actually this week, that's important to us is that people add new functionality all the time, and then maybe if it takes a long time for us to backfill all that information to like rerun over a large series of blocks, that's going to be a big bummer, because we're going to be doing that all the time, or maybe we only do it occasionally and we miss out on sort of new protocols. So it's important to us that the backfills run quickly. So now what we'll do is we basically just deployed up the new ribbon code. So let me just verify that that's running there. I can do, I think K exec deploy MEV inspect. So we're hopping into the Kubernetes deployment here of MEV inspect. And let's just make sure that we have this new ABI to make sure that the code is sort of up to date. We have a ribbon one? We have a ribbon one. Okay, great. So the code is up to date in production. And there's a new command that I'll introduce us to called MEV backfill. What backfill does is it allows us to say, for a block range from starting at this one's 129, 599 to this one, I want to backfill over that range. So basically run all inspectors, all information, rebuild the database, etc., over that range, and then do it with a parallelism of 10. And that 10 is kind of the magic number associated with here. Obviously, it's you can just run the command, and the command will work. But to kind of peel that back a layer, what's happening here is we'll actually take this block range and then divide it up into 10 slices, or if it's uneven, give some a little bit more or whatever, and then spin up within Kubernetes itself 10 different instances of a backfiller who's going to basically run through each of the blocks and backfill the section that they're responsible for. To make that a little bit more tangible, I'll run through an example with 10 here. Let's see. So here we're looking at all of the pods. Pods are basically little packaged up applications. So you can just deploy to Kubernetes, just say, hey, go run this for me, please. So currently the only one we have running is our just main app, which kind of can listen for new blocks. So I'll go ahead and run this block, this backfill. It's 100, is it 100 blocks? Yeah, it's 100 blocks over 10 instances, over 10 parallelism. So if I kick this off, boom, it says it's backfilling. And then we'll start seeing over here on the right, let me zoom out one, that we're spinning up basically all these different containers. And what the containers will do, each of them, Let's see if I can catch one before it ends. I can look at the logs here. Oh, oops, there we go. Oops, let's watch it. We had a block range of 100. Each of them got 10 of them. And now they're all kind of in parallel, just running on some servers right now, taking their 10 and backfilling them into the database, running the latest version of Inspect. So you can see that we're inspecting 100 blocks, and it's taking maybe about 30 seconds or so per thing. So we can make that a little bit faster probably too, but there we go. We just inspected 100 blocks. So in order to do a little bit more analysis, we can kick off a longer backfill to run over Ribbon. And what we'll do is we'll actually run it over that period of time right around when the investor email for its token launch went out. So we can see maybe was there an uptick or was there a change, or how many people started doing deposits, new addresses doing deposits around that range in time. So I think that was, 124, 51500, 124, 57, 500. And we'll do it with a parallelism of 50. How about 50 distinct pods? We'll just let these come up, and then we'll go back into questions while we're waiting for this. This will probably take about, I don't know, maybe 10 minutes or something.
So for the viewers here who don't know, analyzing one block with the Python library before, or the Rust library, or the TypeScript library before it, took much longer than it does here. And certainly analyzing 100 blocks would have taken far, far longer, like on the order of an hour or something like that. And we got through it in under a minute, I think, something like that.
Yeah, 30 seconds or so. Yeah, maybe 45 seconds.
Yeah.
Totally. Yeah, that's an important thing that we're thinking about with the design of Inspect in general, is just for scalability's sake, so that we can iterate really quickly. Sort of new protocol comes out, add support for it. Let's run the backfill. We see the results, we can query it, we can get answers to the larger ecosystem. Cool. Should we hop back into questions?
Yeah, so we got a question here. First, Georges, we'll answer your question live. And then before that, Godokoro says, so if I wanted to analyze the last block's mempool to actually ARB something, I need to build MEV TX pool inspector. Is there a library to do this? So unfortunately, this only works on historical MEV and only analyzes historical MEV. It's not the type of thing that will help you actually arbitrage and capture MEV yourself. So to do that, you would need to build your own bot. If you go to the Flashbots GitHub, you can find the simple arbitrage repository, which will do this in like a very naive way, not in the mempool, but it'll look at the last block and if there are any arbitrage opportunities given the state of the last block. So unfortunately, this won't help you capture any MEV. It just like looks into the past. And then Georgios asks, maybe you can take this, Luke. Georgios asks, what did you do that made things much faster?
What did we do that made things much faster? I'm not sure. I would say...
but what about storing all the traces, Luke?
I guess, okay, sure. Storing all the traces does make it much fast. Well, there's different things that are fast about this, I would say. So there's one component, which is the fact that shout out to Charush. So one of the things that's described in that architecture diagram at the very beginning is that we have both, we have two ways of pulling in that sort of initial information, that trace information. It's one by the RPC directly. When you query the RPC directly, it actually has to redo the work that was done for that block originally to produce the traces, that nice little tree of function calls. And so we have a secondary database which actually just stores the traces raw. So then when we do a backfill like this, not only are we not like destroying the node associated with that RPC URL, instead we're destroying a database, which is much more comfortable being destroyed at scale, basically. So all of these are actually running against historical trace data that's been pre-backfilled into a database at the moment. So that was a major scaling thing that probably cut the amount of time in half, I would say.
And then
because we're not doing nearly as many network calls.
What's going on the right of your screen here? This is parallelized kube pods. That's the other thing, right?
Yep. So parallelized kube pods were definitely a huge component of it as well. So rather than having maybe a single runner where you say, okay, start from here, go to here, and I'll see you in a couple weeks, and you're just going tick, 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 tick. Now we can spin up. So we have 50 different pods running right now. We haven't really pushed this to the max. I bet we could go much farther from parallelism. But yeah, so right now we have whatever 50 distinct pods that are running, each of them taking a fraction of the blocks and doing that process of inspecting, running using the latest code. Yep, those are two major ones, I would say.
Georgios asks, so Godo Koro says, are there any mempool analysis libraries people have released? Maybe. I don't know. Maybe someone in the chat can take that. I'm not sure off the top of my head. And then Georgios asks, do you have any issues where many pods take the same handle on the database?
Where many pods take the same handle on the database? The pods will each get their own connection to the database. So I think we can allow up to 1,000 distinct connections. So this will be 51 connections right now with the 51 pods. So we should be fine on that for a bit. Yep. Yeah.
Are there dependencies in backfilling that would preclude parallelization from A98,000?
From 98,000, like a parallelism of 98,000?
Sorry, the person in the chat called A98,000
so the person
says, are there dependencies in backfilling that would preclude parallelization?
So it's we can keep going as we want. I would say we're in. I was talking to Robert about this earlier. We're in the sweet spot right now where you want to be, I think, with most scalability, which is that how scalable we want to be is just a function of how much we want to pay to have bigger servers, basically. The main knobs that you can twist are that database connection thing would probably become the most bottleneck. I think we're at like 1,000, and I don't really like. Yeah, we'd probably have to think about that most, soon. So we'd say like, okay, we have 1,000 different distinct pods that are running. Each one has a connection to the database. Maybe that becomes an issue. One issue is storage size. I'm hoping that it doesn't happen now, but in a test of running a larger backfill earlier, we actually ran out of memory on the database. So that's a concern, which is real. That was about 2 hours ago. It was a real big shock before going live with this. And then, yeah, I would say the other thing is processing power within Kubernetes. You can scale. The nice thing about Kubernetes is we can scale up. We can just add servers. We even did this kind of earlier. You can just throw more servers into the bucket of Kubernetes, and it lives over a bunch of servers, and you'll just schedule pods across all the servers you want. So you can increase kind of throughput through that as well. So yeah, I don't know, to infinity.
Dordo says, basically we were having gaps in the database because of the many connections to DB, or that was the diagnosis at the time.
You're having gap. Oh, like locking? Are you talking about locking mechanism? Maybe.
I don't know.
That was one of the things I was a little concerned about. Is that because every time you do this, these sort of it's doing a deletion and then an insert, and I think it will take gap locks on the deletions. And so right now we're like explicitly saying they're non-overlapping these queries, but I don't know how smart Postgres is, and that could be an issue at some point.
Yeah, that seems to be what Georgios is talking about. He said yes and yeah. Yeah. I think we're okay I don't know. First time we ran it, sort of fingers crossed, I guess. I don't know, but yeah, it's. I think it seems like it's smart enough on locking, because we're so explicitly saying take this range, take this range, take this range. Yeah. I gotta say, I really like seeing all the pods on your screen there.
I know. Yeah.
I don't know what it is. It's just cool.
My children.
Yeah, farming out.
I know.
there.
Yeah. Should we hop into one maybe? You can do Klog. We can just watch one, see how it's doing so far.
Let's go party with
we're
the
at
pod.
68 out of 120. We're partying with the pods. Let's get another one going, huh?
Yeah.
How we doing? Stream some more.
I don't know.
Ultra
that you're
hacker here.
seeing this. You probably aren't seeing this, but like whenever you do something different on your Vem, I have to like move where I am on camera, where you are.
Oh, really? I need the full real estate.
Yeah. So what's each one of these corners? Tell me about that.
Sure. So we launched the initial command out of the top left, so that's not quite as interesting, that backfill command. Top right, what we're looking at is the live status of all of the running pods, and it's just querying it every 2 seconds to be like, how you doing? So like the case that would be bad that we saw earlier is if we just start on status seeing like error. That would probably mean we either ran out of memory or something, or maybe we started database locking, or the database itself hit like CPU limits, something like that. I don't know. And then these bottom ones, what we're seeing are 2 distinct pods who each have, looks like, so what was that block range? Like 7,000? 6,000?
Yeah, 6,000.
Yeah, so we asked it to inspect a range of 6,000 blocks. And here we are, So each of them got, I guess, whatever. Yeah, 6,000 divided by 50, 12. So 120. So each got 120. And so they're each kind of doing their own work, working through, finding all the transactions, finding the transfers, liquidations, and hopefully some ribbon stuff.
So we're about halfway through. No, we're 3/4 of the way through. So
Yeah,
80 out
3/4 of the way through.
120. Yeah.
Mhm.
So it'll take 12 minutes to get through 6,000 blocks. It's pretty insane, actually.
Not bad. Not bad.
No. Yeah. There a couple months ago there was a 2-week period of time where there was a gap on MEV-Inspect Trust data, and we had to backfill, and it took much longer than 12 minutes. I'll say that much. No
I know.
parallelization. So this is
Well,
a huge,
realistically,
yeah.
how far back would we really want to go? Probably 3 million in like a full backfill, right? That would be like July of last year or something, or 2020, something like that.
Yeah, December
6,000.
2020. December 2020.
Times 12 minutes. This many hours. This many days. 4 days to do the full.
Wow.
That's not so bad right now.
Not bad at all. No.
We'll take it. Assuming, yeah, fingers crossed. I'm still kind of waiting for the database to run out of memory. I won't check it to jinx it, but we'll see.
So,
Any other questions? Yeah.
sorry, not Jan. Yeah, not December. Jan 2020. My bad.
Oh, cool.
Cupid asks, question from the top ARBs from a while back in the stream: was the net profit inclusive of base fee?
In that original query, I think you're right. I think it might have been. Yeah, I think we might have included base fee. So we could fix that. Yeah. So we want to do gas price Coinbase minus base fee times gas. Yeah.
Yeah.
Yep.
Post
Good call.
15.59.
Good
Yeah,
call.
It's probably like some.
Well, it depends. It depends on the lens you look at it, because that's actually still payment from the searcher, right? It just doesn't end up with the miner. Or wait, you were talking about the very first query. We were talking about the most paid.
Yeah, the most paid one, I think.
Yeah, I guess it depends whose perspective, right? From the searcher, they paid that much. From the miner, they made a little less, right?
Oh yeah. So the searcher's personal profit is a little bit less than, well, not even
It's
necessarily.
inclusive
a little
of
bit
base
less,
fee.
but some amount less because we're including base fee in it now. But the miner payment is the miner payment because since base fee.
No, it's all applied from the searcher perspective.
Yeah.
Yeah, because the searcher is actually paying that base fee, right?
Yeah.
So it's still net of their profit.
But it's not a miner payment, right? So you wouldn't include it in the money that the miner gets.
Yeah. I guess it's a little unfair to say minor payment. But yeah, I don't know.
Yeah. Thank you.
We're coming up on it. Yeah, thank you.
If you want to be more helpful, you could submit a PR, but I don't expect you to.
Complain with the PR. That's right. Be the code change you want to see in the world.
You could live code it with us. That
Oh,
could be the
look,
next
we're
one,
starting to get
Cupid.
some completeds over here. This is the most satisfying part.
Yeah.
There we go.
You could get on stream. We could fix it together. You know. Oh wow.
Uh-huh.
Let me move. Oh no.
We're starting to see them complete, hopefully.
Yeah. Okay. So we're getting close to all our pods being done.
Yep. It's like baking.
A little
Pods
bit.
are close to being done.
You can't watch them. Yeah.
I guess, well, we could start looking right now. We don't have to wait for the full, right?
All right. Go
Hop
for it.
into the database. We're hopping in. We're hopping
Oh
in, folks.
god. I need to move you now. Again.
Boom. I'm everywhere. We're all moving stuff. I got the Zoom stuff on my screen. I'm like trying to put aside. Okay. Let's just assume. Well, yeah, this is gonna be fun. So we'll let those finish. Those are gonna finish right now. Let's see. Count star. How many classified traces do we have right now? Or maybe let's see how many we got in that range from classified traces. Where block number. What is it? Greater than or equal to 124,515. It's gonna be real embarrassing if we don't see, if we get like a 0. Block number equals. So that's why the backfill's so fast. So, it's like that'd be a real funny joke. Yeah.
Oh man.
The fact that it's taking some time is fantastic.
Yeah, it probably means we're counting, right?
Yep, probably does. I think this is going to take some time.
Yeah.
Let's see. This actually, I wonder. It actually makes me wonder if we need to speed up this table. I don't know. Is there an index on this on block number? There should be. Block number, yeah. Okay, so that shouldn't actually be that slow. It's all right. It's in it's in recovery from the Vexel. No. Okay, let's look at some stuff. So we'll say select maybe how many ribbon traces we got. I don't know if it's going to protocol. Hopefully these aren't all super slow.
Spin up Kube for your queries, you know.
Parallelize the query. That's supposed to do that for us. That's not on us. Yeah, maybe this will take some time.
This is the not fun part of the stream now. Just waiting for a query.
I know, just waiting for results.
Wow, we still have the same number of people watching us too.
Seriously?
Yeah. Nobody's dropped out.
No dips.
Well, we had like 80 at one point.
This is the squad right here.
Oh, geez, 2 people left after that.
Oh, devastating. They're like, thanks for that's like when Netflix throws up that screen, right?
Hmm.
Hey, you've been watching for a while. It's like, oh yeah, never mind. Maybe we do. We'll just get one. How about just to get a sense?
Yeah, maybe. So Dana Zord says maybe because the pods are constantly updating the index.
Yeah. Well, I think the pods should be done now, right? Let's see. Yeah, pods are done now. So that's good.
Nice.
Which is nice. Oh, what /G? Look at me. I'm in MySQL. X. Limit 1. Boom. Okay, so here we go. Here's the deposit. Oh, that's kind of... Is that... is this always... Oh, it's not always ETH, right?
It's not always ETH.
That might be something that we would want to add. So that's actually a good example of where we make that distinction of like we have the base level traces, so we can classify, decode inputs and stuff like that. But it's helpful to have those tables like transfers and swaps and stuff because of a case like this where it's like, oh, actually this one is in a different. It's not an ETH. It's in something else like USDC maybe or something. It's helpful, but okay. Let's see. That's a bummer we can't get the count. Maybe we can get, well, this is the count of all. What if we, I'm kind of surprised that, because that's in an index, that'd be quick. Yeah, maybe the index, I don't know. I think it's supposed to update as you write. I don't think there's a delay. I don't know. Anyone in the chat? I'm more of a MySQL guy historically. Well, I much prefer Postgres now, I'd say. Damn, that'd be a bummer if we it's not indexed well. Well, I mean, we could just slap an index on the protocol maybe to make this speed up a bit.
Yeah.
Let's do that in the meantime. How about? Oh, there we go.
There we go.
That can be okay. So 2,000. So we got about 2,020 in that 6,000 block range. We got about 2,267 ribbon calls. What should we look for here? Maybe distinct addresses?
Can you look at how they change over time? You should see them like ramp up.
So maybe we look at count group by block number, something like that?
Yeah.
Sorry, this is like so messy too. Whoa. Okay, well, wait, oh, this makes sense. Maybe we group it by, how many? We did 6,000, so group it every 100 maybe?
Yeah.
Is that round -2? This is an exercise for me. Okay, how many do we have here? Quite a few still, right? We have 60?
60, yeah.
One sec, get out of this mode. Boom.
So ideally, I think, there you go. Kind of cool.
So here's the counts over time. Yeah, maybe we do one more up just to see is there anything really noticeable other than just like time of day. Nothing, no major spikes I would say here. Yeah. Is there a specific time that we're looking for? Do we have a timestamp? I don't think so, right? I don't think so.
I don't think so.
Like hustling to do it.
I mean, ideally we'd be able to like compare the previous day to this day, you know?
Yeah. Yeah, if everyone wants to hang for another 10 minutes, we do the previous day. What day of week was it? Was it in the middle of the week?
So
It wouldn't be
I
like a
mean,
Saturday or
like
something?
the block range that we have is like 16 hours on that day, right?
Okay. Okay.
Um,
That should cover it. I would say maybe, I mean, that's a little bigger, but that's not statistically significant.
yeah, no,
It
that's well,
looks
yeah.
looks bigger, but that also could be people sleeping, right? Right.
So I mean, this is kind of the exercise, like
Oh, how about this?
you know,
Count just addresses.
Mevin. Yeah. Oh, that.
Sorry. Give your comment while I'm doing that too. Just think.
Yeah, it'd be funny if we could figure
Yes,
out
maybe.
if this was being,
Oh,
if we could see this being Sybil attacked. But so, I mean, MEVInspect is neutral, right? It simply just classifies traces and then tries to sum those into, or tries to classify those, then tries to infer if it's MEV extraction opportunities or not. And here you can see that we've identified a bunch of these traces on the Ribbon protocol. Thousands of them around the time when that airdrop was announced. And then I think it's on us, it's on the community to then go and, analyze that and see whether analyze that data, see what you can infer from it. So there you go.
this is for each 1,000 block range, the number of distinct addresses that deposit came from.
So moving from like 170 to 210, it's like an increase of 25%.
Maybe something. Yeah. I don't know. It depends what hour of day this is, right? Maybe this is like the sunrise,
Yeah.
something like that. The other thing we could look at maybe is amounts. That'd be kind of cool. Like, what have we said? Like, would we look for amounts that seem like relatively small?
Yeah.
Just like many different addresses that are just doing like $1 in, $1 in, $1 in. I don't know.
Yeah.
Now we're maybe digging too much.
Yeah.
I don't know. Do we want to keep going on this, or I think it shows the concept.
I think it shows how you can get the data out, right?
Mhm.
How you add a trace classifier, and then how easy it is to then be able to pull out structured data on this, and then it's on like data analysts to see whether you can infer anything on that. So in our case, we just did like a 16-hour range on a specific day where like investors, became aware of a coming airdrop. If you wanted to do this in a more robust way, you'd probably like look at a week before that as well as a week after and see if there's any substantial difference in the number of deposits or maybe the distinct addresses like Luke has on the screen there. There's all sorts of stuff that you can do when you are armed with the data to do that. And MEVInspect is just a tool to arm you with that data and to help illuminate the dark forest. So unless there's like any last questions, this is getting to be over an hour and a half at this point. So I appreciate our loyal 60 viewers, but we will try to close after some last questions. So anybody have any questions, folks? Time to make you much larger, Luke.
Time to make me much larger.
Yeah.
What is that? Oh, on the display.
Yeah.
Oh, nice.
Oh,
Yeah, I'll leave that.
there
There
you
you
go.
go. Am I big? Am I big now?
Yeah.
Nice. I was like, what's that supposed to mean? Kind of closing
What's
thought.
that supposed to mean? You know what that means. You got me.
Bigger on the screen.
There's a couple questions. Let me like really quickly alter my camera too.
Mhm.
Yeah. Okay, so a couple of people saying this is amazing, and thank you. So shout out to you, Luke. Thanks for all the hard work and for the stream.
Shout out to the whole squad: Robert, Darush, Guy, 100%.
Everybody involved. Georgios
And
for
maybe
paving the
inspect as a
way.
town. George's for paving the talents, right? Paving the way outs, right?
Scott too. We got one question. Can you filter by DEX?
Yeah, totally. Yeah, well, actually, okay, complicated question. So, yes, so you can filter by ABI always, and the ABI is how we chose to decode it in that moment. For cases like sushi versus pancake versus Uniswap v2, they use the same contract. And so we haven't, because you can just deploy to those at any time, there's, hundreds of thousands of distinct Uniswap v2 pools. We're not able to explicitly say this is Uniswap v2 versus this is sushi at the moment, at least, because we'd need to index all those addresses basically. So yeah, so you can always see which protocol is like v3 versus v2 versus 0x, etc. In cases where the ABIs are distinct, but not necessarily the granularity within the different code or within the same code, shared code.
One question. So there's a question here about Kube, KDB, if we've ever experimented with that.
KDB, that's like the data pipeline, I think, service. I haven't played with it personally, but we did. Yeah, it does. Yeah, we're kind of moving towards that world, though. It seems like where maybe we could use something like that. Yeah, I think it's like a. Yeah, I don't know. I won't try to make any guesses. It's like a data warehouse sort of platform. We were thinking about moving to ClickHouse potentially instead of Postgres for this stuff. But I don't know.
And then Mishiki says, this is not MEV-Inspect related, but I thought I would address it. So Mishiki asks, a bit unrelated, but do you plan to publish the sources of an updated version of the relay? Some parts of the relay, Mishiki, I think there will be updated source code too. Some parts of the relay I don't think will be open sourced. Right now the relay is closed sourced, and the pieces of the relay that are closed sourced and don't match with what the open source version are mostly specific to our infrastructure. Yeah, as well as like some very specific parameters like searcher reputation. Going forward, I expect that like there will be some work maybe around parallelizing the EVM, something like that, that will be closed source as well. And then got a question here about what are the infra requirements to run our own stack of MEV-Inspect?
Yeah, so you can run it on kind of as small or big as you want. What we were saying earlier, basically, if you want faster backfills, you use bigger servers. But to give a rough scope, up until the presentation today, for today we made it a little bit bigger for the sake of querying and backfill and stuff. But we've been running on two T2 smalls on AWS for the Kube cluster, which is like the minimum amount you can do for an EKS cluster, and then just like I think a medium Postgres, something like that. And then I think when we started doing a lot of queries, we upped it to an X large Postgres, just like which is more than we need probably. But all that to say, it's relatively small, depending on what you want to be doing.
Cool. So I'm gonna close it out. Georgios asks about like exposing MEV-Inspect DB over Redash and adding a REST API for it. Definitely want to do that.
Yep.
So just do time. And then I think I'll end with, oh man, now I'm like in front of this. So I got to move myself. But anyway, if you enjoyed this, you want to get involved, here are a couple ways that you could do that. So we would love to see protocol support for other types of AMMs, for other liquidation protocols, asset minting ARM, something that I'm interested in personally. So like minting staked ETH at Lido and then swapping that for ETH on Curve and ending up with more ETH than you use to mint synthetics. Super interested in NFT related things generally, and then like anything that makes MEV generally, interested in having that support. On more of an architecture level, we could use some support for analyzing a single transaction and then analyzing bundles. So that'll be like new types of MEV strategies. You could reason about a sandwich. Someone in the chat was talking about or back running or like more complicated things. And then looking for some help also, people who could help us analyze and visualize this. So showing it on MEV Explorer as one example. I'm always available. May take a little bit to get back to you, but I will try to do so. So if you have questions, feel free to DM me. You can DM Luke. Our Twitter handles are there. Check out our repo if you have any questions or want to get involved. And thank you all so much. Really appreciate you tuning in. This is good fun. Try to do more of them.
Thanks so much, everyone.
Cheers. Thanks, everyone.